Hi students, welcome to Sunil's tutorial. I am Sunil Mirwani and today we will be doing this chapter called as elasticity. Right, let's see what is elasticity. Let us see what is elasticity. Now, the property possessed by a material by virtue of which it opposes a change in shape and size and regains its original dimensions as soon as the deforming forces are removed is called as elasticity. What is elasticity? Elasticity definition. It is a property by virtue of which it's a property possessed by a body by virtue of which it opposes a change in its size and shape and regains its original dimensions as soon as deforming forces are removed. In simple language, if I apply force on a body and if I remove the force, if the body regains its original size and shape, then the body is said to be elastic body. If I apply deforming force on a body, the body is going to get deformed. If I remove the deforming force, if the body regains its original size, shape and dimensions, then the body is said to possess elasticity. Right? Next, if this is elasticity, what is plasticity? What is plasticity? Now there are some bodies which get easily deformed by application of small deforming force and they do not regain the original size and shape when the deforming force is removed. Such bodies are called as plastic bodies. Right? Bodies which get easily deformed by application of small deforming force and they do not regain their original size and shape when the deforming force is removed. Get bodies that get easily deformed by a small deforming force and do not regain their size and shape when deforming force is removed. Such bodies are called as plastic bodies. Fine, do we get this in here? So you have two properties here. One is elasticity, the other is called as plasticity. Right? Now, what do you mean by deformation? Elasticity, plasticity. What do we understand by deformation? What is deformation? Now, deformation, a change in the size and the shape of the body, that is, a change in the dimensions of the body is called as deformation. Any change in the dimensions of the body because of forces acting on it is called as deformation. What is deformation? It is a change in dimensions. It is a change in the dimensions of a body due to forces acting on it. Dimensions of a body due to forces acting on it. That's what is deformation. Okay. Next, what do we understand by stress? Very important word. What is stress? Now, when I apply force to a body, the body gets deformed, right? Suppose if this is the body, and if I am applying some force on this body, the body is going to get deformed, right? How much is the force that is being applied per unit area is called as stress. Stress is defined as the force, deforming force per unit area, right? Stress is defined as the deforming force per unit area. Stress is defined as deforming force per unit area. Deforming force per unit area. The deforming force per unit area is called as stress. So stress is given by the formula the applied force upon area. Applied force upon area. Some authors even say that stress is equal to the internal restoring force upon area. But the internal restoring force will be equal to applied force. So whether I say it as internal restoring force per unit area or applied force per unit area, it is the same thing. Fine? That is what is stress. Next, types of stress. Right? When we talk about stress, there are three types of stress. One is called as the tensile stress, or which is also called as the longitudinal stress. The second stress is volume stress, and the third stress is shearing stress. Right? Now, what do you mean by longitudinal stress or tensile stress? Suppose if I have a body which is connected through a rigid support. Let's assume I have this wire that is connected from a rigid support. Let's assume that this is my rigid support and I have a wire connected. Let us assume that L is the original length of the wire. Right? Let us assume that some force is applied here. F is the force that is applied downwards. Now, because of the force that is being applied in a particular direction, the body being elastic in nature is going to have a change in its dimensions. Let's assume that its dimensions change by a small extent. Let us assume that the change in dimension is, say, L, right? Let's also assume that the wire has a surface area. The wire has a surface area of pi r square, right? So let us consider a wire suspended from a fixed support with a mass m. Let's assume that mass of the wire is, say, m, with mass m attached to the free end. Thus the force that will be acting on the body will be mg. Force is always equal to mg. So thus the force mg acts on the wire. Let us assume that small r is the radius of the wire. So the cross sectional area of the wire is going to be pi r square. Now, by definition of stress, tensile stress is equal to applied force upon area. Right? Applied force is F upon area. F upon A. F is nothing but mg. A is nothing but pi r square. Thus, tensile stress is mg upon pi r square. In simple language, what is tensile stress? A stress that produces a change in the length is called as tensile stress. If the stress produces a deformation in the length of the wire, then that is tensile stress. Okay. Next, let us see what is volume stress. So, I didn't give you the definition of tensile stress. Tensile stress, when the deformation produces in the form of change in length of the body, then it is called as tensile stress. Let's just write that definition down first. Definition of tensile stress: when the deformation produced is in the form of change in length of the body, then the given stress is called as tensile stress. So if the force brings about a change in the length of the body, then that is called as tensile stress. Next, let's see what is volume stress. Like in the case of tensile stress, the stress brings or the force brings about a change in the length of the body. Here, the force brings about a change in the volume of the body. Right? Definition: what is volume stress? The deformation produced is in the form of change in volume. If the deformation produced is in the form of change in volume, then the stress is called as volume stress. Right? Let us assume I have a balloon. If I apply force on it from all directions, then its volume will reduce. It will become smaller in size. Right? That will be the volume. The new volume will be original volume minus the change in volume. Right? Now, a change in pressure can either increase or decrease the volume. Thus, I can say that volume stress, which is equal to all stresses are applied force upon area. So, applied force upon area. Applied force is, how do I apply force to bring about a change in the volume? By changing the pressure. So, this is nothing but change in pressure. Change in pressure is nothing but dP. Thus, volume stress is equal to dP. Next, what is shearing stress? What is shearing stress? If the deformation produced is in the form of change in shape of the body, then the stress is called as volume stress. Is called as shearing stress. Deformation produced is in the form of change in shape of the body, then the stress is called as shearing stress. Right? For example, if I have a cube, if I apply a tangential force to the upper surface of the cube, then what would happen is that the upper surface would move. The whole surface would move, and that would bring about a change in the volume. The upper surface would move by an angle of theta. Right? The body undergoes a change in shape if a tangential force is applied to the body. If I assume that a tangential force F is applied to the body of area A, then shearing stress is given by the formula applied force upon area so applied force is F upon area is A, so that is going to be your shearing stress. Next, now stress therefore can be defined as the ratio of force per unit area. So in that case, what will be the units of stress? Units of stress. Stress is force upon area. Therefore, the SI unit of stress will be newtons per meter square, and the CGS unit of stress will be dyne per centimeter square. Those are going to be the units of stress. If these are the units of stress, what will be the dimensions of stress? What will be the dimensions of stress? Dimension of stress is equal to nothing but force upon area, right? Force is nothing but ma, mass into acceleration, that is mass into displacement upon time square. So the dimensions of force will be m1 l1 t minus 2, mass into displacement upon time square. Area is nothing but m0 l1 t0. Area is always measured in terms of length. Therefore, the dimensions of stress will be m1 l square, l minus 1 t minus 2. So the dimensions of stress will be m1 l minus 1 t minus 2. Right? Do we understand stress? Next, once we know what is stress, let's move on ahead and find out what is strain. Right? What do we understand by strain? Strain is nothing but the change in dimension per unit original dimension. Strain is defined as the change in dimension per unit original dimension. Strain is nothing but the change in dimension per unit original dimension. Thus, strain can be defined as change in dimension upon original dimension. Right? It is a ratio. Okay? Now, what are the different types of strain? Just like stress, there are three different types of strain. Like we have three different types of stress, you have three different types of strain. You have tensile or longitudinal strain, you have volume strain, and you have shearing strain. These are the three different types of strains. Now let's see, what do you mean by tensile or longitudinal strain? Right? What do we understand by tensile or longitudinal strain? It is nothing, strain as such is nothing but change in dimensions upon original dimension. So how do I define longitudinal strain? The deformation consists of change in length of the body. If the deformation consists of change in length of the body, then it is called as longitudinal strain. Deformation consists of change in length of the body. Right? So in that case, if L is the original length of the body and small n L is the change in length due to the force, change in length due to the applied force, then tensile strain is nothing but change in length upon original length. Change in length upon original length. So thus tensile strain is going to be nothing but L upon M. That is what is your tensile strain. Next, what do we understand by volume strain? Volume strain. The deformation consists of change in volume of the body, then the strain is called as volume strain. If deformation consists of change in volume of the body, then the strain is called as volume strain. Right? Now if V is the volume, original volume, and dV is the change in volume due to the applied force or due to the applied pressure, V is the volume, dV is change in volume due to the change in the applied pressure, then volume strain is defined as change in volume upon original volume. Change in volume is nothing but dV upon original volume is nothing but V. That is called as volume strain. Next, shearing strain. What do we understand by shearing strain? Now, when the applied deforming force produces a change in the body, then that is called as shearing strain, or shearing strain can be defined as the ratio of the lateral displacement of any layer to its distance from the fixed layer. I'll write this definition down. It is defined as the ratio of the lateral displacement it is defined as the ratio of lateral displacement of any layer to its distance from the fixed layer, to its distance from the fixed layer. Right, that is what is shearing strain. Right, for example, suppose if I just show you the front view of a cube. Let's assume I have AB is the lower surface, HG is the upper surface. Let's assume that a tangential force is applied to layer HG. In that case, there will be a change in shape. The body is going to change shape by an angle of theta. The upper layer is going to get displaced by a layer of by an angle of theta. Right? Let's assume that it gets displaced to H bar and G bar. Right? In that case, what is shearing strain? I can say that in that case, shearing strain is nothing but it is the lateral displacement of any layer, lateral displacement of any layer to its distance from the fixed layer, its distance from the fixed layer. Right? Now what is the lateral displacement? Guys, see this diagram? The lateral displacement is h bar and the distance from the fixed layer is ah. So I can say this is nothing but h bar upon ah. Right? Can we see the diagram once again, please? I have h bar upon ah. Now guys, in this triangle AH bar, if I apply tan theta, what is tan theta? Tan is opposite upon adjacent. So tan theta would be h bar upon AH. So h bar upon AH can be written as tan theta. But theta is very small for very small angles, but theta is very small. And we know that for very small angles, tan theta is approximately equal to theta. Therefore, I can say that shearing strain is equal to theta. Fine, do you understand this? Next, let's move on ahead. Hooke's law. Now, first of all, before we go on to Hooke's law, let us first understand what is elastic limit. The maximum stress to which a body can be subjected without permanent deformation is called as elastic limit. When you apply force to a body, it gets deformed. When you remove the force, the body regains its original size and shape. But if I go on applying force to a body, after a certain point of time, even if I remove the deforming force, the body does not regain its original size and shape, right? There is a permanent deformation, right? Now, what is the maximum force that I can apply to a body without permanently deforming it is called as elastic limit. So before I go on to Hooke's law, I would first want to define what is elastic limit. What is elastic limit? The maximum stress to which a body can be subjected, without permanent deformation is called as its elastic limit. Right? That is what is elastic limit. Now, coming back to Hooke's law. What is Hooke's law? Hooke's law says that within elastic limits, stress is directly proportional to strain. Simple. The more force I apply, the more will be the change in the dimension. More force, more change in dimension. Put it in proper words, within elastic limit, stress is directly proportional to strain. That is what is Hooke's law, right? So Hooke's law is, Hooke's law states that within elastic limit, stress is directly proportional to strain. Stress is directly proportional to strain. Within elastic limit, stress is directly proportional to strain. That means stress is directly proportional to strain. That is what Hooke's law states, right? Now, therefore, I can say that stress, to convert proportionality to equality, I have to multiply by constant. So, stress is equal to constant into strain. Therefore, I can say that stress upon strain is constant. This particular constant is called as modulus of elasticity. This constant is called modulus of elasticity, right? So thus I could say that modulus of elasticity is the ratio of stress upon strain. Fine, do we get this idea? Now, what will be the units of modulus of elasticity? Modulus of elasticity is a pure number, it's a ratio. Hence, it does not have any unit, right? It will have the units of stress. My mistake. It will have the units of stress. Therefore, the units of modulus of elasticity will be the same as the units of stress. The units of modulus of elasticity is same as the units of stress, because strain is a ratio, it does not have any unit, therefore it will have the units same as the units of stress. Therefore the units of modulus of elasticity will be newtons per meter square in SI units and dynes per centimeter square in CGS units. Those will be the units of modulus of elasticity. Next, what will be the dimensions of modulus of elasticity? Dimensions. Since the units are same as stress, therefore the dimensions will also be the same as stress. So the dimensions of modulus of elasticity will be m1, L minus 1, T minus 2. Right? Do we get this thing clear? Now let us remember one thing, that Hooke's law is applicable only within elastic limits. The law does not hold good beyond elastic limits. Right? Next. Now, there are three different types of stress, there are three different types of strain. Since there are three different types of stress and strain, and modulus of elasticity is, guys, modulus of elasticity is stress upon strain. There are three different types of stress, there are three different types of strain. Hence, there are going to be three different types of modulus of elasticity. Right? Do you get this thing here? What are the types of modulus of elasticity? There are three different types of modulus of elasticity. One is called as Young's modulus. Right? The first one is Young's modulus. Second is called as bulk modulus. And third is called as modulus of elasticity. Fine, do we get this thing there? So thus, there are three different types of modulus. One is called as, not modulus of elasticity, it's called as modulus of rigidity. So, there are three different types of modulus of elasticity. One is called as Young's modulus, the other is called as bulk modulus, the third is called as modulus of rigidity. Right? Now, what is Young's modulus? What do we understand by Young's modulus? Young's modulus, Young's modulus is the modulus of elasticity that corresponds to the change in the length. Thus, Young's modulus is defined as the ratio of tensile stress upon tensile strain. It is defined as the ratio of tensile stress to tensile strain. Right? So Young's modulus would be defined as tensile stress upon tensile strain. Now let us consider a wire of length L, radius R, and let us assume that the change in its length is L. Change in length is L and is suspended by a mass of M. Okay. Now, we know that stress, like we just did this, that stress is nothing but force upon area. Stress is applied force upon area. So for stress is mg upon pi r square. Strain is change in length upon original length. Change in length upon original length. Change in length is nothing but L. Original length is capital L. So thus Young's modulus, guys, Young's modulus is defined as tensile stress upon tensile strain. Thus Young's modulus is defined as tensile stress, that's mg upon pi r square divided by L upon M. Denominator becomes numerator, so this will be mgl upon pi r square L. That is going to be your Young's modulus. Young's modulus is nothing but mgl upon pi r square L. Young's modulus is since only solids possess length, thus Young's modulus is a property of only solids. Liquids and gases do not possess length and hence they do not have Young's modulus. Right? Next, bulk modulus. Right? How do I define bulk modulus? Bulk modulus is defined as the ratio of volume stress to volume strain. It is defined as the ratio of volume stress to volume strain. It is defined as the ratio of volume stress to volume strain. Now let us assume that a body has volume of the body is say V. Let us assume that V is the volume of the body, and an additional pressure of dP is applied on the body, which brings about a change in the volume of dV. Additional pressure of dP applied to the body brings a change in volume which is equal to say dV, right? Now in that case, what will be volume stress? Volume stress is nothing but applied force upon area. Applied force upon area. We had already found out that volume stress is nothing but dP, right? Because force upon area is nothing but pressure, so thus volume stress is going to be dP. Next, volume strain. Volume strain is change in volume upon original volume. Volume strain is going to be change in volume upon original volume, which is going to be nothing but dV upon V. But what is bulk modulus? Bulk modulus is nothing but volume stress upon volume strain. volume stress is nothing but dP upon volume strain is nothing but dV upon V. Denominator of denominator becomes numerator. So this is going to be V dP by dV. So bulk modulus is going to be V dP by dV, right? Solids, liquids and gases all possess volume. Thus bulk modulus is a property that is possessed by both, or in fact all three: solids, liquids and gases. I think we will stop this here for the day. We will continue with this in the next lecture. Thank you very much.